This is class 14 we're working on, part 2. We did a little bit of it at the end of Friday's class. So basically all we had done was come up with the derivative for e to the x and a to the x, derivative shortcuts. So if you remember, the derivative of e to the x was e to the x, and the derivative of a to the x is a to the x times the ln of a. All right, so let's jump to number 10, which is where we left off. Let's write a brief word problem whose answer is 500 times 0.75 to the t. Good. So a patient ingests a drug that that 500 milligrams of a drug that their body metabolizes 25% of per hour. So 500 milligrams of a drug. Good. All right, so what would f prime of t be for this function? Its derivative. Yep. What else? Yep. And what about the 500? What happens to that? That's multiplied as well, yes. The constant multiple rule. So 500 is just a constant multiple of 0.75 to the t, so the 500 just comes along for the ride. And then the derivative of 0.75 to the t is 0.75 to the t times the ln of 0.75. All right, so let's think of f prime here. 500, positive or negative number? Positive. 0.75 to the t, positive or negative quantity? Positive, yeah, because anything to the x, right, is always above the x-axis. So range is positive reals. What about the ln of 0.75, positive or negative? It's negative, yeah. If you remember, the graph of the ln looks like this, and this place where it crosses the x-axis is at 1. Okay. So at 0.75, it's going to be below the x-axis. All right, so I have f prime is 500 times 0.75 to the t times the ln of 0.75. So it's a product of three things: positive times a positive times a negative. So what's f prime going to be? Negative. So f prime of t is negative. So what does this make sense in the context of our problem? How does it make sense? Yes, f prime is negative, means the function f is decreasing. And when we talk about the problem that we wrote to go with that function, the amount of the drug in the bloodstream should be decreasing because the body is metabolizing it. Good. Okay, so we're now going to expand our collection of derivative rules to include products and quotients. So we can do sums and differences. They're really easy. You just do each one separately. But let's try to come up with a product rule by finding d dx of x squared. We know already what the answer is. What's the answer? What's the derivative of x squared? 2x. So let's just do a little experiment. X squared is x times x, right? So if it were true that there were a nice easy product rule where you could just take the derivative of each factor separately, then this would say I could take d dx of x times d dx of x, and I would get 1 times 1, which is not the derivative 2x, right? So I can't do that, right? So the rule d dx of f of x times g of x, if you want to take the derivative of a product of two functions, it is not just f prime times g prime. It's just not true. Quotients of two functions are similarly misbehaved when it comes to finding a derivative. So here is the real product rule. The derivative of f times g, I like to write it this way because it's shorter, f times g prime plus g times f prime. And I'm going to derive it for you since we did a little of this lesson last class. We have a little time, and I can show you why it's true. So I would like to know, what is the derivative d dx of f times g, right? Well, I'm going to use the definition of a derivative, the limit as h goes to 0. So this is f times g prime. Just another notation. Okay, so I'm going to do the limit as h approaches 0 of f times g, all evaluated at x plus h, which is f. This board is not cooperating with me this morning. F of x plus h times g of x plus h. So that's my function f times g evaluated at x plus h. Then I have to subtract f of x times g of x all over h. Okay, so it doesn't get me very far. What I would really like to be able to do is I've got an f of x plus h and a minus f of x. If I could somehow have those together over the h, what would that be? F of x plus h minus f of x all over h. All right. Does that look familiar at all? That is f prime. Yeah, that's the difference quotient. That's the derivative of f. Okay. So I kind of almost have it, right? I have an f of x plus h. I have a minus f of x all over h. They have to, like, I have to do some finagling to try to get them together. And I almost have g of x plus h minus g of x all over h. What would that be? D prime. Good. Okay, so I'm going to draw a picture that's going to help us evaluate that whole numerator to try to come up with an expression that's more helpful. All right, so got a big rectangle. And I'm going to let this be g of x, this distance just to here. And this distance just to here will be f of x. And that's going to cause some lines there. So then, what's the area of the big inner rectangle? F times g. Yep. So this area here is f of x times g of x. Okay. So now I'm going to extend this line f of x, and I'm going to let that represent f of x plus h. And then this line down here I'm going to extend, and that's going to be g of x plus h, which means the whole area of the big thing is what? F of x plus h times g of x plus h. Okay, good. So my expression that I'm trying to come up with a better way of expressing is f of x plus h times g of x plus h. That's the area of the large rectangle, minus f of x times g of x, which is the area of the inner pink rectangle, So when I subtract the two, what's left? This bit, and this bit. So let's see. Yes, the notes are always on Moodle. Yep. What is that distance? It's not h, because this distance is f of x, and this distance is f of x plus h. Don't try to be too fancy. Yes, f of x plus h minus f of x. Does that make sense? Long distance minus the shorter distance is that little green piece that's left over. All right, this little green piece. What's the length of that? Yep, g of x plus h minus g of x. All right. So this green bit, excluding the corner, what's its area? Times g of x, right? The length of that rectangle is g of x. So this is g of x times f of x plus h minus f of x. Ooh, I like having a f of x plus h minus f of x. All right, and then this side rectangle, excluding the corner, what's its area? Times f of x, yeah. That's the area there. That's the area there. What's the area of the corner? Yep. F of x plus h minus f of x times g of x plus h minus g of x. Okay, so go back to the big picture. I'm trying to figure out a better expression for f of x plus h times g of x plus h minus f of x times g of x. So this one represents a large rectangle, right? The whole outer thing. This one is the pink rectangle. And I'm subtracting the two. And what I'm left with are those green rectangles. So I have to add those three green rectangles together, and that gives me the difference between these two. All right, so that means that I now have the limit as h goes to 0. This is all over h. And now the areas of those rectangles, let's see, I've got g of x times f of x plus h minus f of x. Oops. Right. So that's my vertical long skinny green rectangle. My sorry, that's the horizontal one. And then the vertical one is f of x times g of x plus h minus g of x. And then I have the one in the corner, which was the long one, f of x plus h times, sorry, minus f of x times g of x plus h minus g of x. I'm running out of room. Okay, good enough. All right, now we should see some derivatives. This is f prime. This is g prime as h goes to 0, right? Now when I take the limit, I let h go to 0. I have an f prime and a g prime. So I have g times f prime plus f times g prime. And then what happens to this bit of ugliness as h goes to 0? F of x plus h minus f of x. What happens to that as h goes to 0? Goes to 0 because f of x plus h is going to go to f of x. And then f of x minus f of x is 0. Same with the g of x. So what I end up with when I rewrite everything nicely and a little bit smaller so I can fit it all is g of x times f of x plus h minus f of x all over h plus f of x times g of x plus h minus g of x all over h. So I've just rewritten a little bit here. I had h underneath two separate fractions. You can separate them and make it two fractions. It's just the rules of adding fractions. If you have like denominators, you can just add the tops and you would get back to this. Okay. And then this last bit is plus f of x plus h minus f of x times g of x plus h minus g of x. That's all over h2. Now, if I let h go to 0, I get g of x times f prime of x plus f of x times g prime of x plus 0. Product rule. Why, you don't think this is fascinating? Don't ask me that question. I hate that. I told you didn't have to write it down, which means I won't put it on a test. Okay, so the rule in English says that when you're multiplying two fractions, you want to take the derivative, the first times the derivative of the second, plus the second times the derivative of the first. So in two ways, I want to find d dx of x squared. So I have one way, the power rule, right? Real easy. And I get 2x. Or now I could treat it as a product of x times x and apply the product rule. This is just sort of a quick little verification to make sure that this comes out to the derivative we expect. Okay, first function, x, times the derivative of the second function, which would be what? 1, plus the second function, which is x, times the derivative of the first function, which is 1, and I have x plus x is 2x. Checks out. All right, let's do one more. d dx of 7x to the 4th times e to the x. So I'm going to call this the first and this the second. The order doesn't matter, right? Multiplication can be done in any order. So when I take this derivative, I say, okay, the first, which is 7x to the 4th, first function, times the derivative of the second function. What's the derivative of the e to the x? E to the x. So first times the derivative of the second plus the second, which is just e to the x, times the derivative of the first. And what's the derivative of 7x to the fourth? 28x cubed. And I suppose we could try to factor or simplify, but who cares? I'm not sure that factoring would make it any simpler. All right, so the quotient rule, also quotients of two functions, taking the derivative of, also has a special rule, a little bit more complicated looking. It says denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Or bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Or ho-de high minus high-de ho over ho-ho. Or low-de high minus high-de low over the square of what's below. Many little mnemonics to remember it. But I think that once you do like 3 or 4 or 5 problems, it's just going to be in there. All right, so let's say I want to find d dx of 3x plus 2 over negative 2x plus 1. So denominator times the derivative of the numerator. So denominator, negative 2x minus 1, times the derivative of the numerator, which is three. Derivative of 3x plus 2, the numerator, is 3. So I've got denominator times the derivative of the numerator minus the numerator, 3x plus 2, times the derivative of the denominator, which is negative 2, all over the denominator squared. And then this I can definitely simplify. So I have negative 6x minus 3. I guess I'll just write it all out. Negative 6x minus 3 plus 6x, because I'm distributing this negative and the negative 2 at the same time. So I get plus 6x plus 4 all over negative 2x minus 1 squared. 6x's cancel, and I end up with 1 over negative 2x minus 1 squared. Does that make sense? All right, so then the second part, we were supposed to find the derivative evaluated when x equals 4. So how do I get that? Yeah, just plug a 4 in. We'll call this f prime of 4, even though I never named the function f. So if I plug in a 4, I get negative 8 minus 1 is negative 9, squared is 81. 1 over 81. So the next example, I'm supposed to try to find values of x for which the graph of f of x is flat. So a graph is flat when its tangent line is what? All tangent lines are linear. Constant, yeah, or horizontal line, right? Yep. So a function is flat when its tangent line is horizontal, or its tangent line is a constant. Right? What is the slope of a horizontal or constant function? 0, yeah. So I'm looking for places where the derivative of this guy find places where f prime of x is 0, right? Because the derivative is the slope of the tangent line. I'm looking for horizontal tangent lines, that is slopes of 0. All right, so I'm going to let you work on this one for a few minutes. You got to find the derivative of f of x. You'll have to use the quotient rule or the product rule if you're savvy. And then once you get the derivative, set it equal to 0 and solve it. All right, we've got two ways to find the derivative of f. Method 1, we'll use the quotient rule. That's the most common one I saw. All right, so f prime is going to be denominator, which is e to the x, times the derivative of the numerator, which is 1, minus the numerator, which is x, times the derivative of the denominator, which is e to the x, all over the denominator squared, which is e to the 2x. One way of finding f prime. And if I simplify, I can factor an e to the x out of each term in the numerator, and I'm left with 1 minus x over e to the 2x. And then I have some e to the x's that cancel. And I get f prime of x is 1 minus x over e to the x. All right, so that's one way to find f prime. Once you have f prime, which represents the slope of the tangent line at any given x value, we want to know places where the tangent line has slope 0. So we set it equal to 0 and solve it. Two ways to think about this. You could think about cross multiplying. You could think about multiplying both sides by e to the x. Or you could say, I have a fraction that equals 0. The only way a fraction can be 0 is if its numerator is 0. Just ignore the denominator. And you get x equals 1. All right, so method 2. Involves rewriting f of x as a product instead of a quotient. Instead of x divided by e to the x, I could do x times what? E to the negative x. I can take that e to the x, move it to the numerator, and make the exponent negative. Just rules of exponents. So now this says x times e to the negative x, and I can use the product rule instead of the quotient rule. So you can always do this. Whatever's in the denominator, move it to the numerator and raise it to the negative 1. And you can use the product rule if you want. So when I take f prime now, I get first times the derivative of the second. Ooh, what's the derivative of e to the negative x? Yeah, the derivative of e to the x is e to the x. We don't really know how to deal with that negative. I'll just tell you for today. We'll learn why tomorrow. It's negative e to the negative x. So that's first times the derivative of the second plus the second times the derivative of the first. I could factor out an e to the negative x, and I'm left with negative x plus 1. Set that equal to 0, and you get x equals 1. Minus x over e to the x, which is exactly what we got doing f prime with the quotient rule. So this mystery to be solved Wednesday. All right, so I just want to graph x over e to the x and make sure it's flat at x equals 1. Take me 2 seconds. I'm going to use this program called Geogebra. If you haven't seen it, it's really awesome. So this is the graph of x over e to the x, and we have a horizontal tangent line at x equals 1. So just confirming our results. Okay, so we can use the product and quotient rules even if we don't have actual formulas for f and for g. So I'm given values of f, f prime, g, and g prime, all at x equals 3. So I want to find g minus f prime evaluated at 3. So how do we take the derivative of a sum or difference? Take each one individually. So this is just g prime of 3 minus f prime of 3. Right? Super easy when you have a sum or difference. G prime of 3, they told us was 4, and f prime of 3 is -2, so I get 6. Right, g over f prime evaluated at 3. Is this g prime of 3 over f prime of 3? Nope, I gotta use the quotient rule. Right? So g over f prime, I use the quotient rule, and it is denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And then I can plug in all the values they gave me. f of 3 is 5. G prime of 3 is 4. G of 3 is -1. F prime of 3 is -2. All over f of 3 squared, and f of 3 is 5, so 25. Okay, so this is 20 minus 2, which is 18 over 25. Nope. So when you follow the order of operations, we would do the 5 times the 4 and get 20. The -1 times the -2 and get +2. So that says 20 minus 2. Okay. All right, I'm going to let you work on this last one for a few minutes in your groups. Well, not the last one. So we have a fancy function h, and I want you to find the equation of the tangent line at h equals 3. You are still using these values, f prime, g, and g prime evaluated at 3 when you're taking the derivative. All right, let's discuss. So first, I'm going to draw a generic picture of what we're doing. Okay. I find that this helps me a lot. Okay, so here's my function, generic function h of x. I have no idea what it looks like. And I'm going to say, here's 3. I'm trying to find the equation of the line tangent to h at x equals 3. So I'm trying to find the equation of that line. So it's going to have some equation y equals mx plus b. All right, how do you find the slope of a tangent line? The derivative, okay? So m is just going to be h prime evaluated at 3. Okay. So I get the slope by doing the derivative and plugging 3 in. And then I have to find the y-intercept somehow, and to get that, I need another point on the line. Okay. So I need a point on the line. So the easiest point on the line to get is this point, because it's on the line and it's on H, right? It's the point of tangency. That point is shared by the tangent line and the graph of h of x. And it has coordinates 3, x coordinate 3, comma what? 24, which you got by doing what? Plugging it into what? The original h of x. Good. So I have the slope by taking h prime of 3, and a point on the line is going to be 3, comma, h of 3. Okay, so that's all I need. I need h prime of 3 and h of 3. That will be enough to write the equation of the tangent line. So go back over here, and I say, okay, first thing I need, h prime. If I want h prime of 3, I need h prime of x. Once I have it, I'll plug a 3 in. Okay, h of x is the product of x times g of x. To take the derivative of a product, we use the product rule. First times the derivative of the second plus the second times the derivative of the first. Okay, so that takes care of my derivative of my product. And then I can do the plus 3x squared, take its derivative separately, because they're just separated by addition. So then I have plus 6x. So h prime of 3, now I plug my 3 in for all my x's, and I get 3 times g prime of 3, which is 4, plus g of 3, which is negative 1, plus 6 times 3. So I have 12 minus 1 is 11, plus 18 is 29. Thanks. All right, and then so my point is at 3, comma, h of 3, which is going to be 3, comma, when I plug in a 3 into the original h, what do I get? 24, yeah. 3 times g of 3 plus 3 times 9. Yeah. So I get 24. Okay, so I have my point and I have my slope. I could use point slope form. I could do y minus 24 equals 29 times x minus 3. That's the point slope form of a line, which is super easy. Then you don't have to solve for anything. You just circle it and you're done. Or you could put it into y-intercept form, slope-intercept form. So we have 29x. 29 times negative 3, negative 87. And then add 24 to both sides. Negative 63. You could also get that by writing y equals 29x plus b, plugging in 3 for x, 24 for y, and solving for b, and you would get negative 63. Either of these would be considered fine. All right, so if you were to try to take, well, any questions before we go on? Feel okay? All right. So if we wanted to take a derivative of a triple product or a quadruple product, you know, if f of x was the product of 3 functions or 4 functions or 5 functions, the generic product rule I'm just going to use z to represent the last function. It doesn't mean that there are 26 functions. Is going to be f prime times g times h times z plus f times g prime times h times z. So all of the functions times the derivative of the first, plus all of the functions times the derivative of the second, plus all of the functions times the derivative of the third, f times g times h prime times z, until you take the derivative of the last term, f times g times h times z prime. So if I wanted to take the derivative of f of x here, I would take the derivative of the first, the x to the fourth, and I would get 4x cubed. Then I would just leave the other two alone. 3x squared minus 2x times 3x squared plus 2x. Then I would add to that, take the derivative of the middle one, and leave the other two alone. X to the fourth times 6x minus 2 times 3x squared plus 2x. And then add to that, leave the first two alone, take the derivative of the last one. X to the fourth times 3x squared minus 2x times 6x plus 2. And we could most certainly spend some time simplifying it, but I don't really want to. All right, so we have a few minutes to spare, so I'm going to give you just a couple of practice problems. So for each function, find its derivative. So to check, you can take your function in y0, put your original function, x cubed minus x over 2 minus x. And then in 1, have it graph the derivative. N deriv y0 comma x, right? Graph the derivative point by point. And then in y2, put your derivative that you took algebraically. See if the two graphs match. Then you'll know you did it right.